Hello everyone, welcome to the video. Today we are going to solve the problem longest common subsequence. In this problem, we are given two strings and we have to find the length of the subsequence which is common to both the strings but is also the longest. In the previous video, we have solved this problem using recursion and top-down dynamic programming approach. In this video, we will solve this problem using the bottom-up dynamic programming approach. We'll go through the thinking process, we'll write the algorithm, and we'll also go through the code. We will also do a space optimization of the bottom-up approach and we'll also go through the code for that as well. If you are new to the channel, please subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given that there are two strings and we have to return the length of the longest common subsequence. Note that we have to return the length and not the actual longest common subsequence. We are also given that both the strings are in uppercase letters. It is useful for us because now we don't have to deal with the confusion that whether capital A and small a are same or different. So if we consider this example, these are the two strings that we have been given. And the answer to this is 3. Why? Because the longest common subsequence in both the strings is A, D and H, which is of length 3. So if we consider our solution as a black box, we are getting two strings as an input and we have to return the length, which is an integer. So what will our function signature look like? Our function signature will look something like this. Let us briefly recall what all we did in our previous video. First of all, we broke our problem down. If we had two strings S1 and S2, the first one ended at position I and the second one ended at position J, then we could break our problem down in terms of I, j minus 1, I minus 1, j and I minus 1, j minus 1. Thus, we had our recursive relation. Once we had our recursive relation, we wrote the algorithm for it. We also identified the base or terminating condition. The base or terminating condition was when one of the two strings, at least one of the two strings became empty. That corresponded to whether i's value or j's value became equal to -1. Then we also solved the problem of overlapping problems and duplicate calculation. We used map to store the results of the problems that we have already seen. So this completed our top-down dynamic programming approach. The next step is thinking of bottom-up approach. But why do we need to think of bottom-up approach at all? What is the problem with top-down dynamic programming approach? With top-down dynamic programming, this method will be called recursively multiple times. And every method call occupies some space in memory. Since it will be called recursively multiple times for whatever input we have given, therefore, this calling itself will occupy some significant space in memory. To avoid that, to avoid recursion, we want to think of bottom-up approach. Let us now start thinking about the bottom-up approach. In the bottom-up approach as well, we will use the same insight. What insight? That we can use the answers to smaller problems to calculate the answer for the larger problem. But the order will be different. In top-down approach, we moved from larger input to smaller input. By larger and smaller input, we mean the values of I and j. So in the top-down approach, we will first try to calculate for the largest possible input that we have. For example, if these were the two strings given, our first recursive call will be for both of these strings. And then during the recursion, as we keep on calling the recursive method, at the end, we will reach the smallest input or our base conditions where one of the strings become empty. In the bottom up, the order will be reverse. First, we will even try to calculate only for the smaller inputs. And then using this relation or this insight, we will keep on calculating for larger inputs till we reach the answer for both of these strings. That means in the bottom up as well, we will have to calculate and store the results somewhere. What is the information that we want to store? We want to store the information that for this pair of I and j, this is our answer. What data structure can best depict this? It can be the matrix. So this is our matrix. Now what does any particular element at position I, j denote in this matrix? It will denote that if S1 is still some position I and S2 is still some position j, then what will be the length of the longest common subsequence for such combination of S1 and S2? Now, if we fill this matrix, which element will be our answer? Our answer will be the bottom right element, because that will denote the whole of S1 and the whole of S2. So now our aim is to fill this matrix. Now to fill this matrix, we will have to make use of this relation. So let's say we are trying to fill the value at any particular element I, j. Then how will we fill this value? The value at I, j will be dependent on these three positions. Why? Because this will denote I, j minus 1. This will denote I minus 1, j, and this will denote I minus 1, j minus 1. So if we have these three values, we can always fill this value. So how should we fill the matrix? We can fill the matrix row wise, row by row. That means when we reach at this position, we will have all these three values to fill the value at this position. Now let's see how will we start filling the matrix. To start filling the matrix, we will think about our base condition. What is our base condition? Our base condition is that the values of I and j are such that either S1 or S2 is empty. So what can I use in this matrix to denote either S1 or S2 being empty? I can denote them by first row and first column. So let's see and understand this first row. This first row denotes that S1 is always empty. There is not a single character that we have to consider in S1. And S2 changes from completely empty till A, till AE, and so on till the whole AEDFHR is covered. Similarly, here first column will denote that S2 is completely empty, and we are gradually progressing S1 from completely empty till the position where whole of S1 is being considered. So what will be the values in our first row and first column? It will be 0, because at least one of the two strings is empty. So there is no point of length of longest common subsequence. So we can fill all of these values by 0. And what will be the dimension of this matrix? It will be m plus 1 cross n plus 1 if the lengths of the two strings are m and n. So here basically we are considering these strings at 1 based index and not at 0 based index, because for 0 we are representing that the string is empty itself. So now with these observations, we know what is the size of the matrix to declare. How do we start filling the matrix? How do we fill any particular element using previous elements? And what will be our final answer? So we have everything that we need to write our algorithm. So let us now try to write the algorithm. So what will be the first step of our algorithm? We will first declare a matrix of size m plus 1 and n plus 1. Then we will fill zeros in the first row and first column. Now our aim is to fill the whole of matrix. To fill whole of matrix, we have to fill it row wise as we decided. So clearly we will have to iterate and reach at a position I, j, and then try to fill its value. So how will we iterate? In the first iteration, we will have fixed a row, and then in the nested loop for that particular row, we will iterate over columns. So we will be at a position I, j. Now we have to fill this position I, j. To fill value at position I, j, first of all, we will check if the characters at the two positions in the string S1 and S2 are equal or not. To check this, we will check character at I-1 and character at J-1 in S1 and S2 respectively. Why I-1 and J-1 and not I and J? Because If we are at a position I in the matrix, that means we are at the position I minus 1 in the string. Consider this B. This B is at second row in this matrix 0, 1 and 2. But this B is at position 1 in the string A, B, C, D, G, H. Why? Because A is at position 0 and B is at position 1. Therefore, we are using the comparison like this. If it is true, then for filling at position I, j, we simply have to do z plus 1. Z is nothing but the value at I minus 1 and j minus 1, which is just the diagonal element. So we can fill this. Else, we can get the x, which is the value at the left column. We can get the y, which is at the top, and we can get the max of the two. The max of the two will be value at dpij. And in this manner, we will iterate and fill values for all I and j. And we'll return our final answer dpmn. What will be the time complexity of this approach? The time complexity will be big O of m into n. Why? Because we are running two nested loops. And similarly, space complexity will also be big O of m into n. Let us now see the code walkthrough for the same algorithm that we just discussed. You can also find the link to this code in the description. So we get the two strings s1 and s2 as the input, and also the two lengths are given. Even if these two lengths were not given, we could simply calculate them from strings. So we first declare a matrix of size x plus 1 and y plus 1. Then we first fill zeros in our first row and first column as part of our base condition. This is being done through the separate method. Then we iterate over the matrix row wise and we try to fill the value for each I and j. To fill value at I and j, we first check the values of the characters at I minus 1 and j minus 1 position in the strings. If these two are equal, then we fill the value as z plus 1. Else, we get the x and the y and we fill the value as whichever is the maximum of the two. Later, we return dp x, y. To fill the first row and column by zeros, we had this separate method where we simply iterate till max rows and max columns and fill the values as 0. So this is how the code for our bottom-up tabulation approach looks like. So this was the problem where we were finding the length of the longest common subsequence. There could be an extension to this problem where we are asked to print the actual longest common subsequence. So how will we do that? We should be able to figure that out from the matrix, because when filling up this matrix, we would have traced the common characters, and that is how we reached this conclusion that the length of the longest common subsequence is 3. This 3 would not have appeared magically. We would have started from 0 here, and then one by one, somewhere this 0 would have become 1, then somewhere this 1 would have become 2, and then somewhere this 2 would have become 3. So how is this length of longest common subsequence increasing? It will increase because of this condition. Because here, if the two characters at S1 and S2 are equal, that means that character is part of the longest common subsequence. And that is why the length of the longest common subsequence increases by 1 here. So if we backtrack our answer from here till here and then figure out where all we increased the length of the longest common subsequence because of this condition, we can find the characters that were part of the longest common subsequence. And Z, we know, is the diagonal element, because x and y are the top and the left elements, so z is the diagonal elements. So we start from here, we backtrack, and we figure out that from where, in which all places we have come via z. Then we will get our answer. So our path may look something like this. And with each of these diagonal connections, we have added one character to the longest common subsequence. Consider this. Here at this position, it is possible that the length of longest common subsequence is 0. But then two same characters came in both the strings, and here the length of longest common subsequence became 1. So that is what the significance of diagonal connection or this condition is. So we know that we definitely have to iterate and move from our current position to next position in every iteration while traversing in this direction. Now, how do we know what will be our next position? Consider any position. Let's say this one. Now the value at this one would have been filled by either x, y or z. X, y or z. So we know definitely that which one of them has filled this value. So whichever was responsible, x, y or z, we would move to that position. So in this case, like y was responsible, so we move to this position. So let's see what does our overall approach look like. We are backtracking from bottom right to top left in the matrix. That means we are iterating. And what is our goal in every iteration? In every iteration, we will check if that character has become a part of LCS. That means we will check if we have come via diagonal way. If we have, then we will store that character somewhere. And then second goal is to move to the next position. And what will be the next position? It will be dependent on x, y or z. Among these three, whoever was used to arrive at the value of I, j will be our next position. So what all do we have in each iteration? In each iteration we will have I, we will have j, we will have this strings characters si and sj, we will have x, y and z. So let's check the first part, checking if the character is part of LCS. We can use si and sj to check if the character was part of LCS. Let's say it was. If it was, then we have to store it. Now, in which data structure should we store it? Since we are traversing here in the reverse order, we will encounter the last character of the common subsequence first and first character of the common subsequence last. That means the stack is the best data structure to store these characters. So we stored that character in the stack. Now we are done with one. Now our next aim is to figure out the next position. So if the characters were equal, that means we have used z. So what will be our next I and j? Our I minus minus and j will also go minus minus, right? Otherwise, if these two characters were not equal, then we would have used either x or y to fill these values. And which of these would we have used? That is also we know, because our condition was the maximum of x or y. So from the values of x and y, we will know that which of these we have used. And if we have used x, that means we have to go to the top row. So I will be reduced by 1. And if we have used y, that means we have to go to the left column. So j will be reduced by 1. In this manner, we can iterate over this whole matrix from bottom right to top left. And till when we will iterate? We will iterate till I and j are both greater than or equal to 0. And then we can use the characters in this stack to basically print out our longest common subsequence. So what will be the time complexity here? The time complexity will be big O of n plus m. It will not be big O of m into n because we are not going through all the elements in the matrix. We are only moving from bottom right to top left. And the maximum number of steps that we can take from bottom right to top left is big O of n plus m. So this is our final algorithm to print the actual longest common subsequence. Let us now come back to our original problem, the length of the longest common subsequence. And let's see if there is a possibility of optimizing the space complexity. So what has been the space complexity so far that we have used? We have used this matrix as the space. So space complexity is big O of m into n. So our aim is to think that at any point do we need this whole of the matrix in the memory. We are filling this matrix row wise. So consider that at any point in time we are trying to fill this element. The value at this element will be dependent on the values at these three elements, right? So when I'm filling the value at this element, do we need any row that is above this row? No. We only need, whenever we are filling any particular row, we only need the values of elements in that row and the values of elements in the previous row. That is it. So we only need two rows at a time. So we don't need the whole matrix. And how can we represent the two rows? We can represent them by arrays. So our two rows can be previous and current. Current will be the row that we are currently filling. So let's say if we are filling this element, the value at this element, then what will be the three x, y and z on which the value at this element will be dependent? They will be this will be our new x, this will be our new y, and this will be our new z. So we can fill the value of this element. Similarly, we can fill the value of the whole current row. When we are done filling with the whole current row, what will we do? We will move to filling to the next current row. And what will be the previous for that next current row? This same will become the previous. Also, in the next iteration, this previous will become useless because our new previous will be this. So what we are essentially doing is we are iterating. And in every iteration, we have two rows, previous and current. We are using the values of previous and current to fill the current row. And current row then becomes the previous for the next iteration. And previous becomes useless. So what will be our final answer? Our final answer will be when we reach at this position. So what is this position? Our last current's last element. But how will we start the algorithm? Even to start the algorithm, we need some values in the previous array. So we know that for the base condition, first row and first column is 0. That means our first previous row will have all zeros and first element of all current rows will also be 0. So we will use these to be able to fill previous and current. Then we can easily fill them. To fill the current row, we will simply iterate from 1 to m and we will use the values of x, y and z to fill every current element. And this whole bigger iteration, bigger loop will run from 0 to n. So what will be the space complexity here? Now the space complexity has reduced to linear time, which is big O of m or big O of n, depending on whichever string we have chosen in as S1 or S2. Time complexity though remains the same. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we declared the two arrays, previous and current. Then we filled the initial previous array. Initial previous arrays, all elements will be 0 as per our base condition. Then we iterate. We iterate over the length of the first string. And in this every iteration, we will fill a current row. And the first element of the current row will always be 0 again as per the base condition. So now to fill the current row, we iterate over the second string to fill all columns of the current row. Now filling the all columns of current row, we simply use x, y and z and we fill the values of the current row accordingly. So now at the end of this for loop, we have the current row filled as well. Now before moving to the next iteration of the outer loop, we have to copy or we have to make our current the previous. So to make our current the previous for the next iteration, we copy all elements of the current into the previous array. Note that we cannot simply do current is equal to previous. Why? Because that will make current and previous both point to one memory location, which is not something that we want. Current and previous always hold two separate information. So they should always be pointing to two separate memory locations. So once we do that, we can similarly iterate for the next set of current and previous rows. And similarly, we will continue till the end of the first string. And when we are done with all the iterations, we will return with previous y. Or we can also return with current y. Both will hold the same values. So that is the code for the space optimization of the bottom-up solution for longest common subsequence. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.